Hello there! This lecture is going to introduce you to something called the sampling distribution or the distribution of sample means. So we're moving from a distribution where we're just looking at all the possible scores in the population or all the scores within a sample to now looking at every single possible sample mean of a specific sample size that you could get from any given population. So we're really going from looking at x values or scores to means or M, right? Sample means. Because in reality, in research, we typically don't really care about one single person. We're never going to have a sample size of one and try to extrapolate something to the population, right? When we do research, we usually have a sample, and then we compare that sample mean to the population in some of the most basic types of studies. So again, switching focus from scores to means. Now, a lot of the things that you'll see in the example problems are pretty similar to what you did with scores. We're going to have a slightly different formula for z-scores that incorporates the sample mean, and then instead of using the standard deviation, we're going to be using something called the standard error, which is just a measure of the error you would expect between a sample mean and a population mean. Or in other words, it's just a measure of sampling error. So slightly different set of formulas and a very theoretical concept behind what is the sampling distribution. So I'm going to demonstrate the sampling distribution with a really small population and sample size, just to show you what is the contents of the sampling distribution. Because saying the sampling distribution includes every single possible sample mean of a specific sample size from the population may seem pretty abstract, so I'll demonstrate what that actually means. Keep in mind as I go through that example that the sampling distribution has certain characteristics that are set forth by the central limit theorem that makes it so that you don't have to find every single possible sample mean of a specific sample size from the population, because the distribution has certain characteristics that always hold true. Which, as you'll see from the very basic example, if you had a large sample size and a large population, it would be super tedious to go through and figure out every single possible sample mean. So luckily the central limit theorem comes to save the day. I'll also show you a picture of the sampling distribution, and basically just to drive home the fact that now our measure of spread isn't the standard deviation, it's going to be the standard error. Because we're no longer talking about single scores, we're talking about the spread of sample means. And then I'll just go over the impact of the standard deviation and sample size on the standard error. And then the next video will go through tons of examples that'll show you how to do these things in practice. All right, so here is a demonstration of the distribution of sample means. So we're starting off with a very small population, unrealistically small, but for the purposes of this demonstration, it's fine to have a small population. So we say we have 3 people in the population, one has a score of 3, one has a score of 4, and one has a score of 5, on whatever it is we're measuring, whatever our dependent variable is. So you see uppercase N, population size is 3, 1, 2, 3 scores. If you calculate the mean for this population, you would get a mean of 4. And if you calculate the standard deviation for this population, you would get a standard deviation of 0.816. So here's the population that we're starting with. And let's say that we wanted to figure out every single possible sample mean of a sample size of 2 from this population. Remember, that's what the distribution of sample means, or the sampling distribution is. Every single possible sample mean of a specific sample size that you could get from a specific population. So again, chances are you're not going to have a sample size of 2, and you certainly aren't going to have a population size of 3, but for the purpose of demonstrating this, we're going to stick with keeping it simple. Because as you can imagine, once you go through and understand this, it could get very complicated very quickly with larger samples and populations. So the first step, if you were going to construct the sampling distribution based on a sample size of 2, from this population, was you would want to find every single possible 2-number combination of these 3 numbers. And remember, we are assuming sampling with replacement. So as you can see here, the same person could be selected the first time and the second time. So random with replacement. You'll see that here too. So we go, okay, you could have a 3 and a 4. You could have a 3 and a 5. You could have a 4 and a 3, or a 4 and a 5. Or you could have a 5 and a 3 and a 5 and a 4, right? Or you could have a 5 and a 5, a 4 and a 4, and a 3 and a 3. So that's every single possible two-number combination from this population. And keep in mind that we're counting this sample, 3 first, then a 4, as different from getting a 4 first and then a 3. It's every possible combination. What could happen first, what could happen second. Okay, so we've got every single possible sample that you could get with two people with their scores from this population. Then you calculate all of the means for each one of these samples. So 3.5 is 3 plus 4 divided by 2. 3 plus 5 divided by 2 gives you 4. 4 plus 3 divided by 2 gives you 3.5, and so on and so forth. So these would be all of the possible sample means that you could get of a sample size of 2 from this population. Then I just simply took these sample means and placed them into a frequency distribution table. So we've got our means represented here. So we've got, let's see, 5 is right here, and there's only one of them. We've got 2 4.5s. We have 3 4s, 1, 2, 3 of them, 2 3.5s, and then 1 3. So that's the frequency portion of this. And then remember, back when you looked at full frequency distribution tables, you saw how to calculate the probability associated with each score in the data set. So if we were taking a random sample of 2 people from this population, we would have a 1 out of 9, or a 0.111 probability of randomly selecting a mean of 5. When we look at a mean of 4, we would have a 2 out of 9, right? Because there's 9 total samples. So 2 out of 9, or a 0.222 probability of randomly selecting a sample mean with 2 people that was a mean of 4.5 from this population. So that's how you could explain all of these, right? So, all right, 2 out of 9 sample means, any possible sample mean is 3.5, so you have a 0.222 probability of randomly selecting a sample mean of 3.5 if you have a sample size of 2 and you're selecting it from this population. All right, so I also created a histogram with this data, with the means and the frequencies, and you can see that we have a nice normal curve here. And most often your sampling distribution will be a normal distribution. But here in a little bit, I'll show you something called the central limit theorem that tells you exactly when your sampling distribution will be normal. So you don't have to go through this process of figuring out every single possible sample mean of a specific sample size from the population and then create a frequency distribution table and then put it in a graph. It's unnecessary, but I wanted to demonstrate this for you so that you understand what is the contents of the distribution of sample means, or in other words, the sampling distribution. It's all these possible means of a specific sample size from a given population. All right, now let's look at some calculations. And at first, this may look daunting, but I promise you when you actually do this in practice, you're going to be using this formula for the standard error. Not all of this, but I want to show it to you so you understand how closely it's tied to the standard deviation. And luckily, the mean of this sampling distribution is always equal to the population mean. So that is something else that's going to be a nice, helpful shortcut when it comes to plotting your sampling distributions and figuring out probabilities associated with particular sample means. So we're still working with this original population, and we still have a sample size of 2. Now this you've already seen, right? So you've already seen, the score, the first score, the second score for each possible sample, and then the means. And then down here you see I added those means together to get a total of 36. So this would be kind of akin to the sum of x that we were looking at before. And we were using the sum of x as the numerator of the mean formula. Remember that? Well, remember, we're done with x values. We care about sample means. So now, the mean of the sampling distribution, which has this little symbol, the mu with a little m. And just to break that down for you, this is a population mean because this represents the mean for the entire population of all possible sample means. But you won't see this symbol a whole lot because, as you can see with this demonstration, the mean for the sampling distribution is always equal to the mean for the population. So you'll typically see the reference point, the center of the distribution, being labeled as the population mean because these are the same value. So again, remember, when you were calculating the mean with scores, you had the sum of x over n. Well, now we have the sum of the means over the number of samples to figure out the mean for the sampling distribution. So all these means are added up. You get 36. Divide by, we have 9 samples, and you get 4 for the mean of the sampling distribution. Now let's take a look at how to calculate the standard error. And the standard error is similar to the standard deviation. So the standard deviation tells you the spread of scores. The standard error tells you the spread of means. And the calculation for it is very similar to the calculation for the standard deviation. So you can see here, we are going to call this a population standard deviation of the sampling distribution because we have every single possible sample mean. So we're going to call that a population of means from this population. Don't worry if that's confusing. This is very theoretical. When it comes to actually working out problems, you'll see that this is all unnecessary. It's just showing you why this is the standard error is basically the standard deviation of the sampling distribution. Okay, back to it. So this formula should look rather familiar. Sum of squares over n, right? The square root of sum of squares over n is the standard deviation formula. But now we have the sum of squares over the number of samples, and we're going to take the square root of that. So the number of samples, pretty clear, we've got 9, so that's our denominator. But we don't have this value just yet. We have to calculate it using the sum of squares formula. And just like up here, where for the mean that we've been working with in the past, we were doing the sum of x, and now when we're looking for the mean for the sampling distribution, we just replace x with m. You see the same thing in your sum of squares formula. So we have the sum of every squared mean minus the sum of the means, square that value, divided by the number of samples. So very similar to the sum of squares formula, we're just replacing x with m now because we care about sample means, we're done with scores. So this first value here, I take, I've got all of my sample means, I square all of them, I add them together, and that gives me my first value here. Then the second value, just the sum of the means squared, so 36 squared, divided by 9, because we have 9 samples. This becomes 147 minus 1,296, right? 36 squared, divided by 9. You end up with 147 minus 144, and you get 3 for your sum of squares. Then you would plug that 3 in to your standard error formula, and you end up with the square root of 0.333 and a standard error of 0.577. So this tells you that on average, your sample means are going to be plus or minus 0.577 points away from 4. So the same type of interpretation that you've been looking at when you were comparing scores and the standard deviation and the mean for those scores, only now we're looking at means compared to the population mean, so sample means compared to the population mean, and the spread around that population mean is dictated by the standard error. But guess what? Remember before I said you are not going to have to worry about doing all of this to figure out what the sampling distribution looks like. And you're not going to have to figure out all the possible sample means and then square them and do all this to figure out the standard error because there's this beautiful formula that gives you the same exact answer. So you could simply, to find the standard error, take the standard deviation for the population, which is given to you, it's 0.816, and divide it by the square root of the sample size. Be careful, this little n represents the sample size, so that is this right here. So 0.816 is the population standard deviation, square root of 2, square root of the sample size. You end up with 0.816 divided by 1.414, and you get 0.577, just like you did with all this craziness up here. So for our purposes, this is the formula that we are going to use. See the big all caps, use this formula? There it is. So these calculations look kind of scary, but just to keep it simple, the mean for the sampling distribution is always equal to the population mean, and the standard error is equal to the standard deviation for the population divided by the square root of the sample size. Much simpler than doing all this here. But it's important for you to understand where those numbers are coming from. So The central limit theorem is just a set of rules that describe the contents and the shape of the sampling distribution so that we don't have to go through and find every single possible sample mean of a specific sample size from a population. So for shape, the shape of the sampling distribution is always normal if your population distribution is normal. Even if you have a skewed population distribution, your sampling distribution will be normal if your sample size exceeds 30 or is equal to 30. So if your sample size is 30 or greater, it's going to work out that when you find all those sample means, you're going to have a normal distribution. So the only way that you can have a skewed sampling distribution is if you have a skewed population and a sample size that's less than 30. So think about that conceptually. Why does this happen? And just broadly speaking, once you start to have a large enough sample size, you can expect that those sample means are going to be relatively close to the population mean. Because when you have larger samples, you're expecting them to be more representative of the population, so they're going to have means that are closer to the population mean. So you'll start to have sample means that cluster around the middle, where the population mean is. And then on either end of the distribution, you'll have less likely to occur sample means that are farther away from the population mean. So conceptually, that's why this works out. And just think about how important it is to have a normal shape, right? Because we're probably not going to have access to all the raw data from the population and then construct all of these crazy sample means to figure out probabilities of any mean, like we did here, right? This is unrealistic when you have large populations and large samples. So luckily we have this thing called the unit normal table that allows us to figure out specific scores or means associated with probabilities and specific probabilities associated with scores or means. And that unit normal table is only accurate when you have a normal distribution. So thank goodness the statistical gods shined down upon us and gave us this sampling distribution in the central limit theorem where we almost always have a normal distribution. It's a beautiful thing. All right. I already talked about central tendency. For our purposes, we're kind of done with the median and the mode. We really just care about the mean, and the mean for the sampling distribution is equal to the population mean. So when you go to sketch out your distributions, you're still going to put your population mean right smack dab in the middle. Now, variability is a little bit more complicated, but I just wanted to give you every single possible way to describe what is the standard error of the mean. So variability gets it again, the standard error, which is the standard deviation of the sampling distribution. And that's what I demonstrated here, right? Look how similar this is to the standard deviation formula. We're just replacing x values with means. This is also called the standard error of the mean. So now our measure of variability is the standard error and not the standard deviation. And the standard error just tells you the expected, standard, typical, however you want to say it, distance of any single mean from the population mean. So whereas the standard deviation was the typical distance of scores from the mean of all scores, the standard error is the typical distance of means from the population mean. Sample means, to be specific, from the population mean. Okay, so what this really tells you is if you took a random sample of a specific sample size, how well do you think that sample mean would estimate the population mean? Or in other words, how representative do you think that your sample mean will be compared to the population mean? Another thing to say, how much sampling error is there expected by chance? Remember, sampling error is simply a measure of the difference between a sample mean and a population mean. So the standard error tells you how much difference you expect to see just due to random chance. All right. So if you have a large standard error, that means that you have less consistent sample means. Your means are scattered over a wide range, and you could expect a large degree of sampling error. So you're not going to expect that your sample means are going to be very close to your population mean. So that's a large standard error. Remember, with a large standard deviation, you had less consistent scores, more variability, more spread, more differences. Same concept here, only now scores have become means. Small standard error. That means that you have consistent sample means because your sample means are going to be close together. You're going to have similar sample means that are all very close to the population mean for the most part. So if you think about the formula for the standard error. You see it's the standard deviation divided by the square root of n. So mathematically speaking, if you have a larger standard deviation, then you're going to have a larger number in the numerator of your fraction, and overall a larger value for the standard error. Now, conceptually, that makes sense as well, not just mathematically, because if your scores in your population are really spread out, there's a lot of variability, a lot of differences among all the scores in your population, then chances are any sample mean that you take is they're also going to be pretty spread out and pretty different. Because if you've got these people who are all over the place in terms of their score on the dependent variable, then any given sample that you take may or may not include some of those extremes, or maybe you're just going to have a bunch of different people in your sample that look very different, right? Because your population is very different and very diverse. So if that's the case, you're going to expect that you're going to have a larger standard error, and your sample means aren't going to be very close to your population mean in general. So you can also think about it mathematically as the standard deviation is the starting point for this. Because if your sample size is equal to 1 down here, then you have a sample size of 1. You're looking at scores again, right? Because an x value is a score for one person, sample size of 1. So your spread would be dictated by the standard deviation. So now let's switch our attention to how the sample size impacts the standard error. So mathematically speaking, if you have a larger number in the denominator of a fraction, the overall value is smaller. If you have a smaller number in the denominator of a fraction, the overall value is larger. And that's just basic math. So conceptually speaking, if you have a larger sample size, and I've said this before, larger sample, you expect it to be more representative of the population. You expect for there to be less sampling error. So larger sample size, smaller value for the standard error, you're expecting your sample means to be closer to the population mean. Whereas if you have a smaller sample size, then you're going to expect your means to be kind of all over the place, right? Because who knows who's in that sample? They may or may not represent the population, and it's pretty limited information if you have a small sample size. So you would expect more error or more differences between your sample means and your population mean. So this law of large numbers just gets at the fact that when you have a larger sample, you expect them to be more representative of the population, and there's going to be less error. So now let's take a look at the empirical rule that you've seen before, and how now this is a little bit different, right? Because we're no longer working with the distribution of scores, we're working with the sampling distribution of sample means. So you can see that we still work with normal curves, especially now, because when you have a sample that's, 30 or greater people in your sample, you're going to have a normal distribution. Our mean for our population is still in the center, and the z-score for the mean of our population is still always going to be 0. So that has not changed. Now, what has changed is the fact that our measure of spread is no longer the standard deviation, it's the standard error. So when you look at the calculation for your z-scores, so you've got your mean for your sample minus the mean for your population. So if you think about the z-score formula you've been using, you had x minus mu. Well, now we have m minus mu, right? We're just replacing x with the sample mean. So we have the difference between the sample mean and the population mean divided by the difference we would expect to see just randomly due to chance, or the standard error. So that is our measure of spread for this distribution now. And you can see I just recapped the standard error formula here. So when you plot out your distribution and you say, okay, my points of inflection, where my curve starts to go downward, is at one standard error above and one standard error below the mean, instead of one standard deviation above and one standard deviation below. So the z-scores look pretty similar, right? One standard error above the mean has a z-score of 1. 2 standard errors above the mean would have a z-score of 2. 1 standard error below the mean has a z-score of -1. And 2 standard errors below the mean would have a z-score of -2. So this looks very similar to what you've done in the past. It's just we've essentially replaced standard deviation with standard error, and it's implied that your z calculation is based on the sample mean, not x, and the standard error, not the standard deviation. So here's just a summary of the terminology and the notation that I covered before. So we're now working with the sampling distribution. This is also called the distribution of sample means because that's what's in the distribution, right? All the possible sample means of a specific sample size that could be randomly drawn from a specific population. And it's important to mention that specific sample size because remember, the standard error depends on the sample size. And when we did that demonstration of the distribution of sample means, you can see that sample size is pretty darn important. So it is the specific sample size. All right. Then you've got the mean of the sampling distribution, which this is the symbol for the mean of the sampling distribution. But because it's equal to the population mean, we usually just refer to it as the population mean. And the mean of the sampling distribution can also be referred to as the expected value of the mean, because that's the mean that we would expect to see in our sample if our sample was a perfect representation of the population. Which, as you can imagine, and most times, we're not going to have a sample mean that's exactly equal to the population mean. Even if we have a really large sample, we're still going to have some standard error. And we're still going to at least expect our scores to be somewhat different from the population mean. Well, how different would we expect them to be? We would expect them to be within one standard error of the population mean. So the standard error tells you the expected sampling error, or the typical difference between every possible sample mean and the population mean. So if you have a fairly representative sample, then your sample mean will fall within one standard error of the population mean. And for now, you can think about, remember, extreme scores had a z-score with an absolute value of 2 or more. Well, the same thing here. Extreme sample means would have an absolute value of the z-score of 2 or more. And here's a summary of the distributions that we've covered so far. So we had the population and the sample distribution. And so the population distribution includes every score from the population, whereas the sample distribution included every score from the sample. And remember, we talked about, and Dr. Marshall talked about, how the population distribution is typically normal. Most things in nature are normally distributed, where most people fall in the middle, and then you've got some extremes on the high and low end. The calculation for the shape for the sample distribution could really be any shape because if you have a really small sample, it could be a crazy looking shape, even if your population distribution is normal. Then you've got your means, so your mean for your population distribution, the sum of all the scores divided by the population size. The mean for the sample distribution, sum of all the scores divided by the sample size. Then in terms of variability between the population and the sample, so we have the standard deviation for the population and the standard deviation for the sample here. Remember, we try to bump up the value of the standard deviation in the sample so that it's a more accurate representation of the population. Then you have your z-score formulas for the population and the sample here. Both of these have x minus, in this case, the population mean, in this case, the sample mean, divided by the standard deviation. In this case, for the population distribution, we're dividing by the population standard deviation. And for the sample distribution, we're dividing by the sample standard deviation. Well, now we've switched focus to this distribution of sample means. So instead of looking at scores, we're looking at all of the means for all possible random samples of a specific sample size taken from the population. And remember, for the shape's going to be normal if the population is normal distribution, or if you have 30 or more scores in your sample. Again, the only way you're going to have a skewed sampling distribution is if you have a skewed population and a sample size less than 30. Then the mean for the sampling distribution, this is the proper notation for that. And remember, it was equal to the sum of all the means divided by the total number of samples. But luckily, the mean for the sampling distribution is equal to the population mean. And then variability, instead of looking at standard deviation, now we are looking at standard error, and here's the formula for that. Still looking at a measure of spread, only now we're looking at the spread of means instead of the spread of scores. So then you have the z-score formula, which is the sample mean minus the population mean divided by the standard error. So I hope that this table helps you understand where we've been and where we're going, and how where we're going is related to where we've been. So that concludes the theoretical piece of this lecture. Go ahead and try the example problems on the slides, and then watch that example problem video for all of the answers. And it's very similar to what you've done before when it comes to figuring out probabilities and means, because you're basically, if you start with a sample mean, and you need to figure out the probability associated with specific sample means, you calculate the z-score for the sample mean, then you go to the unit normal table and you find the appropriate proportion and tail, body, or mean to z. If you start with a p-value, so a proportion or a percentile or a probability, then you figure out where that probability is in the table, then locate z in the table, and then use z to calculate the mean. Good luck, guys.